Just checking it's recording. Yep. Okay, we started recording now. So I just got a question from Frozer in the chat. Do we have to use MATLAB when doing 3A? Nope. No, you don't. There's no. If you would like to use any other sort of maths package out there to solve it, if you want to solve it by hand, you can. I haven't personally done it by hand, but I suppose it could be done. Yeah, so you don't have to use MATLAB. If you want to use Wolfram, Sage, Mathematica, Maple, any other package which is available to you, that's fine. One sort of slight caveat is I do need to see how you got the results. Okay, so if you just put the results saying, "Oh, this sort of solves to these values," yeah, I do. For full marks, I do need to see. So if you do use some other sort of, let's say you use Wolfram, if you can copy and paste whatever command you used. I don't know whether Wolfram, I'd want to type in sort of how many order conditions you have into Wolfram, but as long as I can see how you got it. Okay, so in terms of this session, as I mentioned, anything you want me to go through, I will. Of course, I have been receiving some questions about the assignment. So what I'll do is I'll start talking through the assignment again. Okay, I'm just going to share my screen. Okay. Right. Can you? I take it you can see a. Oops. I take it you can see the assignment in front of you. Okay. Right. So this is my questions. Okay. So question 3A part 1 seems to be giving a lot of people some difficulty. What I would say is, if I just bring in the notes. So I think I've mentioned this before, but the oh, that's the wrong one. Where am I? Sorry, I'm just trying to find the. Yeah, so there's example 2.4 in the notes. Here we are. Yeah, so here we have all of our sort of 11 in total order conditions. Okay, they're from here. Now I've given you, I say, okay, I've given you the values of C2, C3, C4. Now, I'm not going to tell you what the value C1 is, but it's sort of, it's an explicit method, so I'll let you work out what C1 is. So what you have is you have a value for B2, which is 1/2. So you have B1, B3, and B4 to solve for. So think of the B's as your unknowns. Have a look at the order conditions. So we need 3 equations because we have 3 unknowns to solve for B's. So you know what C2, C3, and C4 is. Okay, so you just got to choose any 3 equations from those to solve for the B's. And then you have some unknowns. So your unknown, if I got a butcher tableau, so here we have a butcher tableau. You're given all of your C values. So C1 is something, which is quite easy. C2, C3, C4. So you're given those. You can solve for these. How many unknowns how many equations you need? You need 3 equations. I'm not telling you which ones, but yeah. So pick the simplest equations you can. Is always a good place to start with. And then we need. We have 5 A values to solve for. Remember that A21 by the row sum condition has to be the same as C2. So you don't need to solve for that because it's already given here. Okay, so we have 5 A values to solve for. So we need to pick 5 equations from here. So is it 5? Yeah, we need to pick 5 equations from these and the row sum conditions that will allow us to solve for those A values. Okay, so you know, there's a bit of a hint on how to do that. You don't need all of these in the solve. So this solve here, the one in the notes, okay, this particular one did require them all. You don't need that for the one in the assignment. You don't need all of them. So identify the ones you do need and then use them, and you should get a solution for this one. Okay, you'll know. I'm not sure whether the solution is unique. There may well be some other set of values for A's and B's which satisfy those order conditions. Okay, it's not something which is of interest to us, because once we've got a method, what is of interest to us is what is the order of that method, how accurate is it. So in 3 part 2 or 3a part 2, determine the stability function for your ERK method. What does that tell you about the order? Okay, look at the number of marks here. There's only 3, so it's not a lot of work. This will also confirm your answer to part A1. That will confirm that you have an order of the Runge-Kutta method that you were expecting. Okay, so that seems to give people some problems. If you are still having problems with that, I would recommend you move on to part B with just any old 4th order explicit Runge-Kutta method, because you can do all of part B and A, and if you actually work out what A is, then there's only a little bit of code you have to change for part B. Okay, does that kind of make sense? Okay, for part B, I did a webinar last week sort of going through this in quite some detail. The changes for this one is that you have a system of 4 equations, and if I go to the first chapter, the notes at the end of the first chapter, it's talk about solving systems of equations. So we have a vector for y as opposed to a single sort of function of a single variable. So we have a vector of functions essentially, and here in the notes there is a program which uses the Euler method, which, think of the Euler method as a first order Runge-Kutta method, essentially is. Okay, a couple of things you have to change. We have a vector of values. You'll have 4. So here we've got 2 values. You'll have 4. Okay, so you'll have 4 values in your y0, and those 4 values are the initial conditions which are given in this second paragraph. In terms of programming, in this example in the notes, which is example 1.6, we had 2 columns for our y matrix, so we had n steps by 2 columns. The reason why there are 2 columns is we had 2 elements in our y array and our f, and therefore our f array. You'll have 4, so you'll need 4 columns, so that number there will need to be 4. And note that wherever we call the y array, we have to call the whole row. So see, that ordinarily for a single equation that would have just been y and n in brackets. So notice, but I'm calling the nth row of that. Okay, so you'll get a, hopefully if that all works, your y array, you'll have 4 columns in your y array. The first column should correspond, wrong one. The first column should correspond to the number is susceptible, second is infected, the third is recovered, and the 4th is deceased. Okay, so if you want to then, for the second part, you want to find what the target infection rate is, the beta target. Okay, so what you do is your second column in y and experiment with different values of beta, solve it. Okay, you want the peak infection rate to be no larger than 2 million. Okay, how accurate you want to get for beta? This is a modeling exercise, so when we are doing modeling, we're not always 100% accurate. So within the reasonable bounds, I mean, what you've got to remember is this, in terms of this local government, this is a guide. This is a sort of you're issuing guidance to a local government to say, okay, we need the infection rate to be less than this. Okay, so it's all very, it is a modeling exercise. So, you know, if you don't start going daft like calculating beta to say 6 decimal places. Okay. Does that make sense for question part 3, part B? Okay, so for this first part, I want you to submit a program. You might want to copy and paste your program onto your Word or LaTeX document if you want, and also submit the program to the to Moodle as well. And I want you to produce a plot for this part 1. So I wouldn't recommend trying to produce a table, because you'll have 100 days. So let's say you used a step length of 1 day, h equals 1, you'll have 100 rows. So it doesn't really tell you much. It's the plot is what gives us more information than that. For the second one, again, I want you to submit your program, and you might want to copy and paste it into your document as well. I want you to say how you've reached, or how you've reached this target value. So what method did you use? There's lots of different methods out there. I'm not giving you, I'm not giving you any limit on what method to do. The most basic, straightforward, is just keep plugging in different values of beta until you get your peak infection rate less than 2 million. That's perfectly valid. Okay, but I'm also looking for a plot of the number of infected using the original infection rate. So that was beta is 0.4, and the target infection rate. Okay, so this will give you some hint on what the target infection rate should be. So if beta was greater than 0.4, what that's going to happen is you're going to have more people are going to be infected very, very quickly. So that's going to increase that peak. So you know that beta has got to be less than 0.4. Okay. Yes, and I want you to produce another plot. So one plot for part 1 and another plot which just shows the infection rates. That's your second column of your Y array, using beta 0.4 and whatever your beta target is. And that will show you what effect the 2 infection rates have on the overall infection. Okay, does that clear a few things up? Is there anything you would like me to revisit on question 3? Max page limit, that's a good question, actually. We've had problems in the past about having sort of students handed in something like 40 pages. Just going to have a look. Is there anything about a max page limit? What I might refer you to is Leader might have an idea of what the page limit is. Okay, because in the past, when you've had to print these out, we've had quite large, submissions. I can't see a page limit here. I just want to see if Leader's got something about a page limit here. Okay. Right, I can't see anything about a page limit. When I've done my solutions, they're not too. I mean, I've only used sort of maybe 4 pages. It's not, and that's without the code. So what I would do is Sophie, I'd refer you to Leader on that question. Is there a page limit? So what we don't want, for example, is I don't necessarily want tables of data for your solutions. Okay, I know in the notes I have included, for example, here. I have included a table of data, but that's more for sort of teaching purposes. Okay, so what I'm looking for is so where I've asked you to apply your methods, I'm asking for a plot of the solution, and I could tell from the plot whether it's correct or not. So if you look in the second page, the same thing with before part C, produce a plot of the solution. Okay, so I'm not looking for. So if you were to use so here we have a range of 0 to 60, step length of 0.1. So, yeah, so you can imagine that 600 lines of table. That's you know, that's not what we're looking for. So I'm not asking you to include any tables in your solution. Quite a vague answer to that question, wasn't it? Any more questions about the assignment? So I'll keep blabbering on if not. Okay, so this is question 4. Derive a 5th order implicit Runge-Kutta method. Okay, so one thing about implicit Runge-Kutta method, Radal method. So Radal 2a, so we let CS be equal to 1. Originally, I think in the printed version that was C2 because I was using a 2-stage method. So however many stages you have, now I'm asking you to derive a 5th order. So Radal methods. So an S-stage Radal method has order 2s minus 1. So you can kind of work out what S is going to be. Okay, so you know how many stages. So you set CS to be equal to 1. The other coefficients are the root of this. I've used MATLAB in the notes to calculate the roots of that. If you don't have to use MATLAB for this as well. So the same question applies to the previous one. You could use any method available to you to solve. Okay, so find the roots of the Legendre polynomials. So the S, PS, and PS minus 1. Find the root. That'll give you your C values, and your B and your A values are chosen to satisfy the B and C ordering conditions. Okay, so there's a similar example in the notes. Yes, Sophie, so that's correct. So you set CS to be equal to 1. So that's a change in the printed version in the notes. Okay. So we set CS. I'm not going to tell you what S is. It's fairly easy to work that out. So your other C values are the roots. Your A's and B values are using those order conditions, which at the beginning of the chapter, where are we here? Now, in the example in the notes, when we had a look at a 2-stage method, if you halve 2 and round down, or sorry, a fourth, what was it? Was it a 3rd order method? I think our L1. Okay, we want a 5th order method. Okay, so for CK, half 5 round down is 2. So L equals 1 and 2. So however many stages you have, you'll have S lots of equations when L is 1, and you'll also have S lots of equations when L is 2. If, for example, you had 5 stages and L was 1 and 2, you'd have 10 equations from C, and you'd also have 10 equations from D. Okay. Spoiler alert: it's not a 5-stage method. Okay, I'm not going to tell you how much that is. So for each one of L and for each one of I, you evaluate the C order condition, and similar for. Oh, sorry, we don't use a D one, do we? Okay. So for J, you'll have up to K, so you'll have 5 order conditions there. Sorry, 5, but we've got up to S order conditions because we're only summing up to S. Okay, for C, you'll have K times S order conditions from C, and that's solved using MATLAB or any other software available, and you'll get order conditions. And you'll get the solution for A, B, and C. For part B, I wanted to use the pen and paper. The reason being is because it's kind of it's simplistic to do it, and MATLAB can do it in a few lines, and also you're not really learning much about it. So with the this question, it's a stability function of an IRK method. So cover that in the notes. Work out what page number it is for you. Yes, so page 51, equation 4.7, that's your stability function for an IRK method. Okay, and there's your A, B's and C values. State whether it's astable or not. So to be astable, the roots of your denominator got to have positive real parts, and this function here, which is made up of the numerator and denominator of your stability function, that has to be got to be greater than or equal to 0 for any real number y. Okay, and if that's the case, we can say that's an astable method. And finally, part C, if I go back to implementation of Runge-Kutta methods, there's quite a lengthy example here, 3.6. Obviously, this is a hand calculation. I never recommended doing by hand, so here's some MATLAB code. Okay, so you'll notice it's similar to the other code, even the Euler method code. So there's lots of similarities. You define your ODE function, define your parameters, etc. The difference between this and the explicit Runge-Kutta method is we have to iterate to calculate the stage values. Okay, so notice big Y. Okay, so this is these are the stage values, and this so this is a quarter. This is one of our A values. That's A11. That's A12. Okay, so this code in the notes will work for this. You might have to change a couple of things. Again, it's a second order ODE, so you have to rewrite that as a system of 2 first order ODEs. Okay, so remember we let y1 be y, y2 is y dash, y3 is y double dash, etc. But in this case, because it's only second order ODE, we only need y1 and y2. Okay, so the same thing applies to question 3. So you'd have 2 columns in your y array. You'd have 2 values in your y0 array, and we'd have to use the comma colon after the yn. Okay, so we have to also adapt this to solve a system. And one other thing I should say about this implicit Runge-Kutta method, okay, this is a particular type of method, which means we can save some effort when calculating the stage values. So this will work, this for loop here will work for this method, but we can improve on that. So if any of you take this code, okay, do something to it, you can improve on that, you'll get extra marks. Okay, so full marks are awarded for efficient code. This will work, so you can still get a solution using this, but there's a particular benefit of a method of this type, and it's stated in the notes, so I'm not sort of hiding anything from you. It is stated in the notes what that benefit is, and then you can adapt your code appropriately. Okay, and for this one, I want you to produce a plot of the solution. So again, I'm not asking for a table, and I want you to comment on the validity of this IRK method used to solve this IVP. So what is it about your plot that means this method is particularly suitable for solving it? Okay, so that's a bit of that's where I'm looking for a particular insight, or for you to notice something about the plot for that. Okay, so that's a bit of me rapping on about the assignment. Are there any further questions? No? Okay. Right, so last week, if I bring up the Moodle area, so if you look at last week, it was all about direct methods. So direct methods to solving linear systems equations. So we're kind of changing tack now. So we're going from ODE solvers, now we're going to solving linear systems. And the reason being is linear systems pop up loads in ODE work. Okay, so we looked at direct methods. Okay, and on this week's webinars, okay, I've already put out the videos. we're going to be looking at what's called indirect methods. Okay, and I've also put up the solutions to the tutorial exercises from week 4. Okay, so this is a MATLAB live script with all the solutions in. So unless anybody has got a particular thing they want me to go through, I thought I'd just revisit the direct methods because these are bound to pop up on the exam. Okay. So I'm just going to go to direct methods in the notes. Okay, now I want to have a revisit LU decomposition. So I'm going to do another, I'm going to make up off the top of my head another example. Okay. Oh dear, I've got too many windows trying to find out which window is which. Okay. You'll find out if you ever have to do a webinar. It can be quite tricky arranging things your end. Okay, right. So I thought I'd do through an example. Can you see sort of like a blackboard type thing in front of you? Just double checking with you. Anybody? No, you can't see that? Yep. Okay, thank you. Right. I've always got to check because you never know what I'm seeing is the same as what you're seeing. Okay. So what I thought we'd do is have a look at LU factorization. And this is I'm just going to make up a system. Okay, so let's say A, Z, that's my coefficient matrix. 8 and minus 7. I know this has got a nice solution, so I say I've made it up the top of my head. This is kind of just random, and I've chosen these B values so that it has a nice solution. Okay, so we're going to solve this, and we're going to do it with partial pivoting. Okay, so what we have to do with partial pivoting is ensure that our pivot element is the largest out of all the ones below it. So here you can see our first pivot element is 1, but we have a 4 down there, so that's not the largest. So what I'm going to do is perform row operations. So remember from the first year, performing row operations does not change the system. So I'm going to swap row 1 with row 3. So that's a rubbish arrow. So 4, 1, 1, 1, 5, and 1, 3, 2. Okay, so that one now, that 4 is in the pivot element and it's a larger one from any below it. So our next pivot element is this one here, and you can see it's clearly less than 3. So I'm just going to swap rows 3 and 2 around. So the first row is unchanged. Second row 1, 3, 2, and 1, 1, 5. Okay, so our row swaps to we've performed partial pivoting. We also have to do the same for the identity matrix. So doing the same row swaps. So swap row 1 and 3 around, and swap rows 3 and 2 around. Okay, so remember, this is our P matrix, so this is our permutation matrix. If I was to multiply our original A matrix by this P matrix, I'd get this matrix, so the effect of the matrix after row operations have been applied. Okay, so that's our first step. Okay, the next thing I'm going to do is just going to bring in the notes again. Okay, so and we're going to be using these two equations here. Okay, so that's something I'm going to just keep referring to. So that's on page 81 in the notes. So those are given to you. I mean, it's not something I'm expecting you guys to remember. Okay, so we start with our first column. So j equals 1. So our u11 is equal, in the first row, it's just equal to A11 because we do have a summation, but that summation doesn't quite exist yet. Right, so that's A11, and remember we're using this matrix now. So A11 is 4, L21 will be 1 over U 11 multiplied by A21. So that's a quarter times 1. So that's a quarter. And L31 is 1 over U11 times A31. So that's 1 quarter times 1 as well. Okay, move on to select a different color. So if we move on to J is equal to 2, so now we're on the second column. So that was our first column. Now we move to the second column. Okay, A12 is, sorry, U12 is equal to A12, which is 0. U22 is equal to A22 minus, and this is where our summation comes in. We've got L21 U12. Okay, so I'll just show you where that was from. So that's this summation here. Okay, so I in this case was 1, so K is just 1. But sorry, I was 2, so in this case K is just 1, and J was also 2. Okay. So we have, in this case, A22 is 3 minus L21, which was 1 quarter, and times U12, which is 0. So that makes it easy. That's just 3. Okay, and L32, because we're in the lower triangular region now, so A32 is in the lower triangular, so it's 1 over U22 multiplied by A32 minus L31 U12. So it's going to be 1 over 3 times A32 is 1 minus L31 is a quarter multiplied by U12, which is 0. So that makes that easy. Pick a different color this time. I'm running out of colors to pick. Now go back to, I'll go white. Okay, so J equals 3. So now we're on the third column, and we've only got the U values to calculate. So we've got U13 is equal to A13, which is equal to 1. U23 is equal to A23 minus L21 U13. Okay, you start to get used to the pattern in the subscript. So A23 is 2 minus L21, which was 1 quarter, times U13, which is 1. Okay, so that's 2 minus 7/8. Okay, just make sure I've got my arithmetic correct. Hopefully that is. So U33, okay, so we've got quite a few here. We've got A33 minus L31 U13, but we've also got L32 U23. Okay, because K was 1 and 2 in the summation. So A33 is 5 minus L31 is a quarter. That's multiplied by U13, which is 1. And we have L32, which I'm looking around for it. Where's L32? That's 1/3. Multiplied by U23, which is 7/8. Okay, I'm going to reach my calculator at this point because I don't trust myself. So 5 minus quarter minus 1/3 times 7/8. And that's 107 over 24. Yuck. Okay, so this is my so this is the LU factorization. So L is 1, because remember our main diagonal elements of L is always 1. So L21 was 1/4. L31 was also 1/4. 0, 1, and L32 was 1/3. And U is the same as the first row of A, so 4, 0, 1. I'm going to have zeros in the lower triangular portion. U22 is 3. U32 is 1/3, and I'm hoping that 107/24 is correct. Okay, I don't suppose anyone spotted a mistake there. So what we've got is 2 minus. If I get yes, yeah, thank you, Amrit. I was kind of thinking that looks a bit, I don't know. I mean, you shouldn't always expect decent numbers. Yes, so 7/4. Yeah, so that should have been 7/4. So I'll redo that calculation. And we get 25/6. Whether that's better, I'm not sure. So that's 25/6. Okay, so that so that's our LU factorization, and remember we've got P as well. Okay, so what I'm going to do is just off screen, I'm going to just write that down because I haven't got it. Well, actually, I could cheat. I'll just see if we get the same thing using MATLAB. So, by the way, I haven't done this one before, so we might not get the same one. Sometimes MATLAB uses a slightly different approach. Nope, got the same. 1.75. So that 1/3 there. So U23. Why did I put a third? So it should have been 7/4, shouldn't it? Okay, so just checking it with MATLAB. As you can see, I've got the same. So the LU command in MATLAB, as you can see, does the same thing. Okay, so just double checking, but we're all consistent. Yeah. So, okay, that makes it easy. So when I wipe this screen now, I can I have something to draw upon. Okay, so what we just shown is for L. 1/4, 0, 1, 1/3, 0, 0, 1. U 4, 0, 0, 0, 3, 0, 1, 7/4, and we had, was it 25/6, and we had a P 0, 0, 1. Ooh. 1, 0, 0, 0, 1, 0. Okay, so remember we're solving AX equals B, and A is LUX, and we've also applied permutation to A. Okay, so what that means is we have LUX equals PB. The reason being is the inverse of P is itself. Okay, so because if we swap rows around, the inverse is just swapping them back. Okay, so we're solving this. So if we let y equals ux, so the first thing we do is solve. We solve ly equals b, pb, sorry, and the second step is solving ux equals y. Okay, so let's do the first step. So L and that's times by y equals PB. Well, PB is quite easy to calculate because what you do is for the first row you look at where the 1 is, and the 1's in the third column, so that means we use the third value for B. And I don't quite recall what our third value was. So it's going to look very messy. I'm just going to put the second layer back on. So it's 15, 8 minus 7. So I'd make a note of that up here. 15, 8 minus 7. Okay, so if I was to perform this permutation matrix on this, I'd have minus 7, 15, and 8. Okay, because first is so we have 3, 1, 2 is the order. So 3, 1, 2. Okay, so this gives us y1 is equal to minus 7. y2 is equal to 15 minus a quarter y4. So that's 15 plus 7 over 4. So I'm just going to, which is 67 over 4. And y3 is going to be 8 minus a quarter minus 7 over 4. So that's plus 7 over 4 minus a third times 67 over 4. Which is 25 over 6, which is kind of familiar. So that makes it, that gives us a hint that the next one's going to be quite easier than I expected. Okay, so the second step is solving for ux equals y. That's going to be for x. And our y we just calculated, minus 7, 67 over 4, and 25 over 6. So 25 over 6 times x3 equals 25 over 6. So we got a nice solution for x3. Oops. For x2, we have the coefficient of x2 is 3. So if we divide by 3, we got 1/3. And we get 67 over 4, which is that number, minus 7 over 4 times 1. Okay, so 67 over 4 minus 7 over 4 is going to be 60 over 4, which is 15. 1/3 of 15 is 5. You can see I kind of engineered the solution in the end to be hopefully quite nice. Okay, and for x1, the coefficient is 4, so that's 1/4. Minus 7, we've got 0 x2 and minus 1 x3, so it's a quarter of minus 8, so it's minus 2. Okay, so there was an example of using LP factorization to solve a linear system, and this is a very common method, especially used in ODE solvers. So one thing I'll just do is bring in MATLAB for a sec. I'm trying to find a MATLAB. Where's my MATLAB window gone? Give me a sec, I'll just bring in a MATLAB window. Okay, so I'll just make the font size a bit bigger so you can see. So one thing I'm going to do is I'm going to make up a very quick ODE to solve, and let's say t plus y, very simple. Ooh, he says very simple and he makes a mistake straight away. And give it a domain and give it an initial value. Okay, so that's defined an initial value problem. What I'm going to do is use an implicit method to solve this. Okay, so this is one of MATLAB's built-in methods. It's called ODE23S, and I'm going to use it to solve that that method. And I'm also going to ask it to output some stats. Okay, so I haven't really covered how to do this in my part of the course. Okay, so this is ODE23S. It's an implicit method. Okay, and this is how we use MATLAB's own solvers. So if I run that, you'll see we got some output. Okay, and what you can see down here, notice we have in solving this, MATLAB used 33 solutions to linear systems, and it actually used 11 LU decompositions. So within implicit methods, we often use LU factor decomposition. Okay, so you can see we had to calculate 11 LU decompositions, and we had to use them to solve 33 solutions of linear systems. Okay, so that's kind of like, you might be thinking, hang on, I thought this was an ODE course. Why am I suddenly doing linear systems? But that's the reason why. Okay, so that sort of gives you a bit of a background. Okay, was that all right for everyone? So hopefully that gives you just a bit of an extra additional example, and also went through some elements of the assignment. Okay, does anybody have any questions? I'll take that as a no. Remember, you can always email me questions, or you can send them to me via Teams. Okay, right. Yeah. Okay. Yeah. You can. You can always send me questions via Teams. So I think we'll call it an end to this session. One thing I would say is check out the week 5 of the Moodle area for week 5. I put up some videos. These are all about indirect methods. If I'm honest, there's not a lot to really say about indirect methods. We've already looked at them with the Jacobi method for implicit Runge-Kutta method. So we'll start to wind down a bit now for this unit, and you've obviously got the assignment to be working on. Okay, so thanks very much, guys. I'll see you next time. Make sure I stop the recording.